So the previous few days' lessons have been about using the disk method to find volume, right? The disk method happens when the cross sections are circles, right? And when they're circles, like we know that the way that the disk method works is we really just take pi times the integral of radius squared times the thickness. And the reason that we do that is that the area of a circle is indeed pi r squared, and then we're just multiplying by some sort of thickness, right? So now we're moving on to something called the washer method. And we know that we use the washer method when our cross sections are not circles, but rather, I mean, to be honest, are rings or washers. And what I hope to impress upon you right now is that this really shouldn't be difficult as long as we can identify what the area of a washer is. Over here we had circles, the area of a circle is pi r squared, it wasn't a big deal. Over here we just need to talk about if I have a circle with a circle cut out of the middle of it, what is the area of this sort of ring shape that's going around? And hopefully you recognize this is really pretty simple. If we just recognize that there is an outer radius, which I'll call big R, and an inner radius, which I'll call little r, we can recognize that the area of a washer is just pi big R squared minus pi little r squared. And then, you know, that pi is the same and it's a constant. I can just pull that pi out and find that the area of this washer is pi times the big radius squared minus the little radius squared. So, long story short, if you've revolved something around like you saw in the past video where we did lots of examples, and the cross sections are washers or rings like this, like the steps that we take are going to be the same as we did in the disk method. Step 1 was to identify thickness, right? Step 2 is where we identified the radius. The only difference here is that there's going to be a big R radius, which is the outer, and there's going to be a little r radius, which is going to be the inner radius. Step 3 was bounds. And step 4 was where we used our formula. Over here, our formula was pi r squared times thickness. Here, it's going to be pi times the integral of the outer radius squared minus the inner radius squared, again, times the thickness. So my hope is that you'll see through the example I'm about to do that these problems are really very similar, so long as you're willing to draw a careful diagram and you can identify what the outer and inner radii are. So I'm going to go to the next slide where we're going to look at one example of this. So I want us to consider the region bounded by f of x is 6 minus 2x. So I'll just start on that right now. 6 minus 2x means you're up 6. And you're going down 2 over 1, down 2 over 1. We'll see if I can actually connect those. That was pretty good. Okay, so I've got that function. I've got the line x equals 1, so that means this. Wow, I'm like on fire with straight lines today. And the x-axis, so that's this one down here. So the region we're talking about is this sort of triangular shaped region here. I want to take that and I want to revolve this around the y-axis, right? So let's sort of go through these steps, right? Step 1 is thickness, right? Because this is just like the previous videos, I would expect that we could do this, right? What should the thickness of these cross sections be? Well, because I'm revolving around the y-axis, my thickness should be dy. 2, this is where I need to come up with the big R radius and the little r radius. Right? I really feel like it's valuable for us to draw these things in. I mentioned before that the idea on finding these radii is that it's all about starting at the axis of rotation and going from there, passing over the first function, and going to the second function. This is going to be your big R outer radius. Right? And I just realized I didn't actually take a minute to have you guys visualize this. If we took this triangle and revolved it around the y-axis, I hope you recognize that we'd sort of get a volcano shape. You'd sort of get a cone with a hole out of the middle of it. And so that means that the outer radius, and this is always going to happen, is going to go from the axis of rotation, past the first function, and over to the next function. So the question is, what is that distance? Right? Because I'm measuring it side to side, and I hope you remember this from the previous videos, it means you're going to need to change your function from being y equals 6 minus 2x into being an x equals function. So if I move things around here a little bit, I'll get y minus 6 equals negative 2x. That'll give me negative 1/2 y plus 3 equals x. So this distance here is negative 1/2 y plus 3. And you may remember from yesterday, we would always do like the right function minus the left function. In this case, my left function is 0, but for the sake of completion, this should be this minus 0. Sorry, I'm pressed for space there. So my outer radius here is negative 1/2 y plus 3. That's my outer radius. What about the inner radius? Right? The inner radius, again, I find by drawing from the axis of revolution in until I hit the first boundary function. Right? So what is that distance? Well, again, it's whatever the right function is minus the left function. Well, my right function is 1. My left function is 0. So that internal radius is 1. So inside radius is 1. Right? Next step down, third step, is where I'm supposed to find the bounds. Right? Well, because this is in terms of y, because this is in terms of y, I'm looking for y bounds. Because I drew this rather carefully, I think we can tell that this point of intersection here corresponds to 4. This point of intersection down here where it ends corresponds to 0. So my bounds go from 0 to 4. The final step I have to take in setting this thing up is using the formula that we sort of defined on the other page. I'm going to try and scroll this up a little bit so I can fit this underneath all of this work here. Step 4. Right? We have pi, the integral from 0 to 4. Then we have the outer radius, that's negative 1/2 y plus 3 squared, minus the inner radius, which we found was 1 squared dy. And this is the integral expression for the volume. We could compute that. I'm not going to run all the way through it in the interest of time, but I'll sort of stop here and say that that's what the integral expression would be. If you wanted to work this out, keep in mind you need to FOIL this. Once that was FOILed, you could subtract 1 off of it, then you would integrate, plug in 4 and 0, and you'd be done with it. So that's one example of a washer method problem. This one in particular was revolving around the y-axis. In the next video, I'm going to do one that's going not around the x-axis, but that's going horizontally. So I will see you in that one.